Okay, so these two questions here are actually going to lead us pretty well into conservation of energy, which we're going to talk about today. Okay, so the General Lee, when it's about to make its jump over the big creek, okay, requires 1,200,000 joules worth of energy. Okay, it seems like a lot, but okay, we're just going to calculate how fast it's going. Right, so we're going to say that all of its energy then at that point will be kinetic energy because it's moving very fast and it's on the ground at that time. So EK is going to equal 1/2 mv squared. Actually, we'll just say mv squared because there's really no change here, so we don't have to indicate that it's final. Okay, and we're just going to solve for v. So we're going to divide both sides by half of m, okay, and then square root in order to get v. So v will be the square root of 1,200,000 joules divided by 1/2 times 1,500. Right, 40 meters per second. Give you some idea. That's 144 kilometers an hour. Okay, an easily attainable speed for such an incredible car. Okay, 144 kilometers an hour. Okay, all right. Now, here's the thing that kind of leads to conservation of energy. In the perfect physical world where no energy would be lost to air resistance and friction and all that other stuff, the General Lee would have 1.2 million joules worth of energy throughout its entire jump. The only thing that would change would be how much of it is kinetic and how much of it is potential. Because it doesn't jump straight across, okay? It jumps in an arc. Okay? All projectiles follow an arc. So as long as it's not losing energy to air resistance and friction, okay, which are the two places where we typically lose energy to, it would have the same amount of energy the entire way through the jump until it lands on the other side. Okay? Meaning that if one side of the creek and the other side of the creek are equal in height, it'll be going exactly the same speed when it hits the ground on the other side. And that would be true in the perfect physical world. Obviously, in the real world, it's not true because energy is lost and there's all kinds of other complexities. Okay, but we simplify things a little bit for our purposes. Okay, all of the energy is conserved. Okay, and so it just turns into potential energy as it goes up and then back into kinetic energy as it comes back down. Nope, they had drivers. Yes, almost all of those jumps involved a stunt driver. Almost all of them. Not everyone, but most of them involved a stunt driver. Okay, yeah. So yeah, being a stunt driver would have been a tough job on the body. Okay, and how does a stunt driver grip a steering wheel? Besides tightly. How do you grip a steering wheel? Like this, right? Or hands at 10 and 2, thumb underneath. If you do that as a stunt driver, you end up with broken thumbs. You put your thumbs over. Okay? Otherwise, you get broken thumbs. You get broken wrists sometimes, but usually they would have like a plate that would keep their arms straight. Yeah. Well, the problem is when you land, you'd like to try and keep the car straight, which would involve you having to have your hands on the wheel. Yeah. Well, they do still have wheels. They're just not always connected to the axle when they land. Yeah. Okay. All right. So we're simplifying this a little bit. Obviously, the General Lee would still have kinetic energy at its highest point because it's still moving horizontally forward. But we're going to simplify and say, hey, how high was it if it jumped straight up in the air? How high could it go? Okay. Well, if it could jump straight up into the air, which would be a neat trick, it could actually reach a height of 85 meters because we would say all of its energy would then be potential. Okay, of course, then it would fall straight back down, and that would be bad. All right, but we just divide both sides by m times g, okay, and we'd be able to calculate the height of the General Lee were it to jump straight up in the air. Okay, calculating exactly how high above the riverbed it gets is something we would do in Physics 20 in projectile motion. Okay, everybody all right with work energy theorem? Okay, from the looks of your quizzes this morning, I think that's starting to be a little more understandable for us, so that's good. All right, let's look at conservation of mechanical energy. Okay, so conservation of mechanical energy goes hand in hand with work energy theorem. All right, so if you recall, very first day of this unit, we talked about the laws of thermodynamics. And we said the first law of thermodynamics was that energy can't be created and it can't be destroyed. And that's true for all kinds of energy, including mechanical energy, okay, which is what we're going to deal with most in physics. So I can't create it, I can't destroy it. So the only way for something to get energy is for what to be done to it? Transfer, which we know as work. So we have to do work on something in order to give it energy. Then that object or system has the ability to do work on other things. Okay? But the amount of work that I do, if I do 500 joules worth of work on a system, the system can do 500 joules worth of work on other things, one thing, many things, doesn't matter. Okay? That's how much energy it now has. Okay? That 500 joules will always be somewhere. Okay, even in the real world, okay, where there's friction and air resistance and all that, that 500 joules of energy is always going to be somewhere. It's not always going to be doing useful work, but it's always going to be somewhere. Okay, if we're talking about the real world, the places it ends up usually is heat, sound, light, okay, things like that. The kind of wasted forms of energy, the byproducts of lots of energy conversions. Okay. We're going to deal with mostly utopian physics here, okay? That is ideal, perfect physical world, no energy ever gets lost to anything kind of situations just because it's simpler to deal with for right now, okay? So when energy is transferred to an object, it can cause a change in both the kinetic and the potential energy at the same time. Now, we never did any work energy theorems where both kinds of energy changed because you don't have to in Science 10, okay? But do understand that if I do work on a system, I can change both its kinetic and potential energy, right? Which is what the engine of the General Lee does when it launches the General Lee off of the jump. Okay, it's accelerating it and making it go higher. So it's changing both its potential and kinetic energies. Okay, all right. So any change in either one of those means that there's a change in mechanical energy. Okay, because mechanical energy is the sum of kinetic and potential. Okay, so if I want to calculate the mechanical energy of an object, I add its kinetic energy and its potential energy together. Okay, so if we're looking at this example here, if I have a 0.30 kilogram baseball thrown in a straight line, so not upwards, not at an angle, straight, okay, which, is that possible? It's not possible to throw something perfectly. Yeah, it always is going to arc downwards. Okay, but we're just going to say, for simplicity's sake, it's thrown in a straight line. Okay, or we're only dealing with like one instant in time here. Okay, so it's 2.5 meters above the surface of the Earth and is moving at 20 meters per second. So does it have potential energy? Yes. Does it have kinetic energy? Can I calculate how much of each? Yes. Okay, so that's what we're doing here. We're saying the mechanical energy is its kinetic plus its potential. We have a formula that calculates kinetic, 1/2 mv squared. We have a formula that calculates potential, mgh. Okay, we just plug in our numbers. So we go 1/2 times 0.3 times 20 squared, and then we add that to 0.3 times 9.81 times 2.5. Right? So we have 60 joules of kinetic. We have 7.36 joules of potential, which means we have 67.4 joules of total mechanical energy. Okay, they've done something called significant digits. Yeah, well, yeah, it's rounding to preserve accuracy. This number here, the 60.0, is only measured to the tenths position, but this one is measured to the hundredths. But if I add them together, my answer can't be more accurate than my least accurate measured value. Okay, so that's why they've, yes, rounded it, because they need to reflect that this number is the least accurate one. Okay, all right, so I want you guys, that's pretty straightforward calculation there. I want you guys to try 8 and 9. They're pretty much exactly the same. Sorry, 8, 9, and 10. Okay, they're pretty much exactly the same. Give them a try, and then we'll walk through them together here. Okay, so in physics a lot, we deal with really big numbers. And sometimes we don't want to write the whole number, or the whole number is more information than we can be certain of, so we make it smaller. So if I have, let's say, 1,234,567 of something, okay, and I don't want to, and I can only have it, yeah, okay, I can only have, let's say, 3 decimal places, or I can only have 3 digits, okay, then obviously I can't write the whole thing. So what we do is we put it in what's called scientific notation, which always makes any number I'm dealing with turn into a number between 1 and 9.9. Okay, so it's always going to be like a single digit with a couple of decimal places. All right, so that means that in this number, the decimal is right here. But if I want to make it scientific notation, I need to move the decimal all the way to here. Everyone follow me on that? Okay, in our numbering system, every time I move one place forward, I'm moving how many times? 10. Okay, because our numbering system has a base of 10. All right, so if I move this thing this way, I'm going to move it 1, 2, 3, 4, 5, 6 spaces. That means I write this number as 1.23 times 10 to the 6, because I moved it 6 places of 10. Okay, I moved the decimal 6 places of 10. So really this is saying multiply this number by 10 to the power of 6 and you have the actual number, right? But it allows me to represent it as a smaller number, okay, and thus reflect maybe accuracy or something like that. Maybe I'm not certain about these numbers. Maybe I didn't actually measure these. I got them as a result of doing some math and they appeared there, but I didn't measure that accurately, so I have to cut it off here, okay? Everyone kind of follow me on that? So scientific notation really just takes a really big or a really small number and writes it differently. So I could have like this, 0.0002468, okay? And I want to write that in scientific notation. So that means I need to make it a number between 1 and 9.9. So I move the decimal 1, 2, 3, 4 spots. And now I write this as 2.468 times 10 to the minus, was it 4? Yeah. 10 to the minus 4, okay? That means if I multiply this by 10 to the minus 4, I'll get that actual number, right? So that's what scientific notation is. Okay, how are we doing on, can we go over 8 and 9? Okay. Actually, I think I have, nope. Okay, so 8 and 9. If I'm looking at question number 8, okay, we've got the clam, 300-gram clam. What does that need to be in? Does it need to be in grams or kilograms? Kilograms. Okay. So if I want to calculate the mechanical energy of the clam, I need to take its potential and add it to its kinetic, which means M times G times H plus 1/2 mv squared. Okay, so pretty simple calculation there. I take my 0.3 kilograms, multiply it by 9.81, and multiply it by 30 meters. Okay, and then add that to its kinetic energy, which is, okay, 1/2 times 0.3 times 8 squared. Okay, so when I do that, I should get 97.89 joules worth of mechanical energy. Everybody all right with that? All right, now the other two ask you to use this formula, but to not solve for EM, but to solve for one of the others. Okay, so they've got a 55 kilogram high jumper in number 9. Okay, I'm just going to erase what I've got here. Okay, they got a 55 kilogram high jumper, and they're telling you how much mechanical energy they have, and then they're telling you their speed and asking you to calculate their potential energy. So they're saying, yeah, use this formula. Well, not equals, plus EK, but they're saying solve for this now. Well, if I want to solve for EP, what do I have to do to EK? Yeah, subtract it over to the other side. So the mechanical energy minus the kinetic energy should equal the potential energy. Okay, so that'll be 3,000 joules. Okay, that's 3.00 times 10 to the 3 minus 1/2 times 55 times 8.33 squared. Okay, so when I do that, I should get 1,091.85 joules. Right? So that's how much potential energy they have. Now, if it was me asking that question, I wouldn't stop there. I would now ask you, how high above the ground is the high jumper? Okay, but how do I get that 2.02 meters besides that I wrote it up there on the board? Okay, what did I just calculate here? I just calculated potential energy. All right, so this number here equals M times G times H. Do I know the mass of the high jumper? Do I know the acceleration due to gravity? Can I calculate H? Yeah. Okay, so I take my 1,091.85 joules, I divide it by 55 times 9.81, and that'll leave me with the height of the high jumper. Okay, so just like one extra step, not a difficult step, but one extra step on there. Okay, it'll tell us they are 2.02 meters above the ground, which is an impressive high jump. Okay. All right, how many people are done number 10? Okay, I'm going to give you a few more minutes on number 10. Okay, and then we'll go over it. So, okay, instead of asking us to calculate potential energy in 10, they're asking us to calculate kinetic energy. All right, so we're going to subtract EP over. So we'll have mechanical minus potential equals kinetic. Okay, and that'll mean that in this case we have 1,880 joules minus the mass of the hammer, which was 2 kilograms, times 9.81 times 50 meters. Okay, and that's going to equal our EK. All right, so we'll have 1880 okay, minus 2 times 9.81 times 50. All right, so 899 joules worth of kinetic energy. All right, the next step on that, of course, that I would ask would be how fast is the hammer moving when it's 50 meters above the ground. All right, so we know that this number here equals 1/2 times mass times speed squared. So if I want to get the speed, I divide both sides by 1/2 of m. Okay, and in this case, the m is 2 kilograms. Okay, and then what do I have to do? Square root, because v is squared. Okay, so then I take my 889, I divide it by 1, essentially, because that's half of 2, right? And then I square root it. So really all I have to do is square root the 899, right? So it's going 30 meters per second. You would not want to be standing under that hammer. It would kill you, okay? Wouldn't just hurt. Probably wouldn't hurt. In fact, it would probably just be quick. Yeah. All right. That making some sense? Oh, it would definitely change the shape of your toe in an undesirable way. Yeah. Like it would be really, really, really flat. Even through steel toe boots, I would imagine from that height. Flat Stanley. Flat Stanley, the cartoon character. Yeah. Okay. I want you guys to try this one. See how you do with this one. It's a little bit of work energy theorem, but it's also a little bit of conservation of mechanical energy. Okay? There's not really much math to do with this one. It's pretty straightforward in terms of the math, but the understanding part is what I'm really looking for here. Okay? So you got an average force of 100 newtons, pulls back a bowstring on a bow and arrow 1/2 meter. Okay? The bow is aimed vertically. All right? So we want to calculate the work done on the bow, which is pretty straightforward. Okay? How much potential energy is in the bow, how much kinetic energy the arrow would have when it leaves or is released from the bow, and what the potential energy of the arrow would be at its highest flight in the air. Okay, how many of you are looking at that? Like part A, I would assume everybody's got part A done, right? You just had to go force times distance, right? It's 50 joules worth of work. How many other calculations do you need to do? None. You do not need another calculation for this. It's just like the General E thing I was telling you about before. Okay, it had 1.2 million joules of energy no matter where it was in its flight because of the law of conservation of energy. So if I put 50 joules worth of work into the bow, then I put 50 joules worth of potential energy into the bow. When I release the bow will exert a force through a distance on the arrow, transferring all 50 joules worth of potential energy that I put into it into the arrow. So the arrow will leave the bow with 50 joules of kinetic energy. It will then fly vertically, converting all of that kinetic into potential. When it gets to its maximum height, how fast is it going? 0. That means all of its energy will now be potential. And there'll be how much of it? 50 joules. Okay? So it's a question with 4 parts. It requires only one calculation as long as you understand the law of conservation of energy. Okay? Maybe as like a multiple choice question, not as a problem because there's just not enough there. Okay. but it's not hard enough to be a bonus question. A bonus question needs to be a bonus question because it's hard. I don't ever put bonus questions on. It's hard enough to finish the test on its own. The last thing you need is one more question to mess with you. Relax, decompress. Yeah. But people do put pressure on themselves. That's why I don't do it. Okay. We already did that one. Okay. So, couple of things here, guys. Okay, the law of conservation of energy says that the amount of mechanical energy possessed by an object is the same at any point throughout its flight. Okay, so if I drop a rock, okay, over the edge of a cliff, when it starts out, it only has what kind of energy? Potential. Okay, and as it falls, that potential turns into kinetic. All right, halfway down, some of it is potential, some of it is kinetic. At the bottom, all of it is kinetic, but the sum of all of those numbers is always going to be whatever I had at the beginning as potential energy. That's what the law of conservation of energy says. Okay, that's essentially like how a roller coaster would work. If it worked in the perfect physical world, you would always have the same amount of energy anywhere on the roller coaster. But obviously the roller coaster operates in the real world, which is why you never have a hill as high as the first one. Okay, you get towed to the top of the first one to give you the mechanical energy necessary to complete the entire track. If they try to make another hill as high as the first, you'll go down, up, and not get there. And then you'll fall back and do this until you run out of energy. Okay. Yeah, there's a few, and it's got a loop in the middle, right? Yeah. They have that at Knott's Berry Farm. It's called Montezuma's Revenge at Knott's Berry Farm in California. Yeah, and then drops you. Yep. Yeah, you could do the loop a couple of times and then you quit because you're going to run out of energy, right? You're just not going to get all the way there each time. Okay. All right. So that's what we really need to understand there, guys. So tomorrow, okay, we're going to pick up with some more conservation of energy stuff. We'll spend Friday, Monday, probably Tuesday. We'll do another lab. Okay. Wednesday, we'll finish up this stuff. I'll do a unit exam review middle of the week next week. Okay. So that we're all ready for our unit exam. Okay. There's less. Yeah, there's more problem solving and less multiple choice. Yeah.